We will actually do the introductory portions of mixtures today, which is after that video material, but hopefully if you watched that video, you also saw that you were supposed to just look at 12.3 for general understanding. It doesn't get tested per se. We do have an open extra credit and the semester surveys is there. They give you 2 points extra credit towards your final grade. It closes on the 11th, meaning there's no way I'm going to get named the 12th earliest. Giving your final exam is on the Monday. After that, I will hopefully have the points in by then. But if anything, your percent will get a little higher once the points go in. I really prefer students to know what their grade is when they walk to that final exam, but there might be a couple missing points until I get it. Quiz 13 is currently open. It does close on the 11th, 11:59 p.m. Don't forget about it because it's a free perfect quiz score. It's only rated for completion, so go in there and do your best. 45 questions, 60 minutes. For some reason you run out of time, that's fine, as long as you put effort into it, you'll get the 10 points. Exam 4 is this Thursday, 5:30 p.m., 60 minutes. Last time that most of you are going to lab 162. 44 multiple choice questions, cumulative for the semester, and I really want to save Wednesday for review for that, so hopefully you've already looked into that 100 multiple choice question review. We do have an extra credit item that's open for exam 4. That's Sales Site 2 activity that Cody sent you an email about on the 2nd. That does close on the 9th tomorrow, so if you want to do that, if there's those points you haven't started yet, I wouldn't suggest waiting until tomorrow night. It's something that does take a little bit longer, it's not just a quick survey. Final exam for your class, like I mentioned, next Monday, the 15th, 11 to 1 for most students, and most students are in this room, not Clapham. Cumulative for the semester, there are 2 booklets. Each booklet has about 40 multiple choice questions in a time base of 55 minutes. I do have some lecture activity problems there to finish up at 102 instruction. And don't forget about your Google exam 4 homework. Anything you have thought of since we last saw each other? Good? Okay. We were looking at hybridization last time, and so we're picking up, or this was left off. I'm pretty sure it was left off at number 24, looking at boron, before that beryllium. Well, we're now looking at our methane again, which is brought up in number 25. The process to explain the hybridization of CH4, but we had already gone through that. I like to just use this slide to emphasize the fact that it is all about the number of electron groups. They also have ammonia on the slide, and I worked out the hybridization for both of these. They're both tetrahedral bases. They both have 4 electron groups. The only difference is in the ammonia and H3, 1 electron group is a lone pair instead of a terminal atom. Notice how the hybridization, the sp3, is the same. It's not about what the electron groups are, it's simply about the electron groups, how many there are. You can see in the ammonia that the lone pair is actually using one of those hybridized orbitals. So we are still sp3 hybridized because we have 4 electron groups. Any questions? Also remember, you don't have to be able to do this. It's really over here. 1, 2, 3, 4 things. I have 1 S and 3 P's. That gives me 4 things. sp3. Just like our boron and then being sp2 because there are 3 electron groups, 3 fluorides. Flying with free zoning. This is right underneath number 26. In general, a sigma bond and lone pairs of electrons utilize hybrid atomic orbitals. We see that in the ammonia. The lone pairs is one of those hybrid orbitals. To determine the number of hybrid atomic orbitals needed, you simply count the number of sigma bonds and lone pairs. Well, that gives you, that's the same as finding the number of electron groups. So make it even simpler. How many things are attached to that central atom? Here we had 4. We did have 3 sigma bonds and 1 lone pair. Our ammonia gave us 4. In our methane, we had 4 sigma bonds to give us 4. Either way, it's still the number of electron groups. Any questions? In 27, it brings up water, and then it brings up OL2. Well, how many electron groups are there in water? How many things are attached to the oxygen? You got 2 lone pairs and 2 terminal atoms, right? 4. So if you're thinking about the hybridization in your water, there are 4 electron groups. Therefore, our hybridization is sp3. 1 S and 3 P's gives us 4. sp3 hybridized. Everything on the sheet right now is a tetrahedral base. Goes with the base structure, the number of electron groups, to get the hybridization. Any questions? I have something next that's not in the electroactivity book, just because I remember we said when we did expanded octets, we said we'll see in the next chapter as to where those extra electrons end up going. I'm throwing out sulfur hexachloride in advance. We know we are attaching 6 chlorines to our sulfur. I started with our electron configuration, and then I just did the orbital diagram for the 3rd energy level there. Notice we're going to promote or excite 2 of the electrons. One from 3s, one from 3p, to get up to 3d. Meaning, in order to have 6 attachments, we need 6 orbitals to mix together. We have 1 3s, or 1s, we have 3 p's, and 2 d's to give us 6. So the sulfur ends up being sp3d2 hybridized. When we mix those wave functions together, we get 6 equivalent hybridized orbitals. But again, you don't need to go through the process. You always start at S, there's only 1 of those available per the quantum number rules. Move on to P, there's only 3 of those available per the quantum rules. Quantum number rules, meaning if you have to do expanded octet, meaning going beyond 4 electron groups or 8 electrons, then you have to go into D. So to expand octets, they make use of the D sublevel. Notice in the original electron configuration, we don't usually write the D, but it doesn't mean it doesn't exist. So I just wanted to show you something with an expanded octet. The author didn't include that. Any questions? Yes? This is theory again. This is we're trying to understand why nature does what it does. Okay, so we're assuming this is kind of what's happening. Everything to do with wave functions, quantum numbers, everything is all theory, trying to help us understand why nature works the way it does. So yes, we're assuming it doesn't always happen. Diatomic hydrogen, right? Just 2 s orbitals coming together, or diatomic fluorine, 2 p orbitals coming together. But in order to understand why we have equivalent strengths and lengths for bonds, we have to think about what could be happening. Does that make sense? Okay. We obviously can't see things at that level, so all of it is really trying to interpret data and understand and make theories. I hate to use the word theory over again, proposals as to what might be going on. Any other questions? Last time, I know I already mentioned sigma bonds, I wanted to give you a little reminder about a sigma bond, because if you turn to page 290, did I miss a page here? Pages are probably upside down. It's in my hands, that's why it's upside down. 295, we're on 294, sorry about that. At the very top it says a pi bond. So I want to give you a reminder of what a sigma bond was. So a sigma bond was our end-to-end, or if you prefer, head-on interaction, like 2 cars crashing. Well, we're now going to explore what double and triple bonds are. So in number 30, it says a pi bond, or a covalent bond formed by sideways overlapping orbitals with the electron density concentrated above and below the place of the nuclei of the bond in left atoms. This also means a pi bond does have a node or a portion of overlap where there is no electron density. These are also the off here. That's our sigma bond there, okay? For a pi bond, we have side to side orbital overlap. And the easiest way to envision that is think about 2p orbitals. When instead of head-on, they're going to sideswipe each other. Or they're sliding in ice and going to crash like this. Meaning we get the merging of lobes up here and lobes down there. We cannot put a pi bond immediately between 2 nuclei because we already have electrons there for our sigma bond. Meaning head-on interaction can't really be used to describe or understand what's making up a double or triple bond. However, if we put electron density above that plane and below that plane, then we could get another 2 electron share. Probably better than my doodle. So here we're looking at 2p orbitals. together this way. Therefore, we get the overlap on the top and the bottom. Notice, so we get in the middle here, the green, all that green is all sigma, so the yellow is now the pi bond. That right there is a double bond. I know it looks like a triple. It's a double. Each pi bond has electron density in two areas. Can we use hybrid sp atomic orbitals or any hybrid orbitals to make a pi bond? No. Because remember, they have a different shape. And if we want to have a strong bond, meaning one that we're thinking this is why they are strong in nature, we need to have equal electron density above and below. So our hybridized orbitals, whether they're sp or something else, always have uneven loads. They're not balanced, however you want to think about that. Meaning we have to use unhybridized orbitals to make our pi bonds. I think I might have another click. So both ends must give us an equal electron density, therefore we want something like that. Another representation. For some people, this was like, oh, that makes sense, or what I doodled didn't make sense to you. Any questions? We have a little table coming up, so it says pause point. So in number 32, they have a table there for you. We can add to our model for our three types of bonds that we were talking about before, but now incorporating sigma and pi's. So for our single bond, we know that there are two electrons, and we also already said that one sigma bond equals a sigma bond. Meaning, transcribing from the Lewis theory of saying single to the valence bond theory of saying sigma, it's a one-to-one relationship. We're still sharing two electrons. It's now in that plane right between the two nuclei. And of course, it's going to be a pi bond. A double bond consists of a sigma and a pi, which is why a double bond in terms of enthalpy is not simply two sigma bonds. Remember, if we multiply the bond enthalpy for a carbon-carbon single by 2, we do not get the bond enthalpy for a carbon-carbon double. There's different types of interaction going on. And a triple bond, sharing 6 electrons, always consists of a sigma. Every bond consists of a sigma, but then we have two pi bonds. We have the above and below, and then you can imagine turning 90 degrees. This is harder to draw because you have to think about it coming out of the board, meaning another p orbital this way, and so you get electron density in front and behind. We'll have better pictures in a second. So you get this wrapping of the sigma. Then you can break up in number 33 what we had already talked about at the end of the last chapter. Sigma bonds are stronger than pi bonds. It's this table you complete above, consistent with what we observed, the table below. That table. So here we're still looking at our carbon-carbons. Now we are understanding that that is a sigma bond there versus having a pi for the double versus having two pi's for the triple. This is hopefully helping us understand the difference in the energies. Type of orbital overlap is different. Any questions? We do have two examples on the next page. Yours are black and white. I have color, a little bit easier to understand. So for your 1 in 34, that is C2H4, I want to give you the Lewis structure, because that's more familiar. That is two carbons double bound to each other with two hydrogens on each carbon. And again, in this image, all the sigmas are green up there. So we are having hybridized orbitals from the carbons overlapping with the s orbitals from the hydrogens. What would be the hybridization on those carbons? We have 3 electron groups, right? Hydrogen, hydrogen, and everything else attached to that one carbon. Other one, hydrogen, hydrogen, everything else. So we need 1 s, we need 2 more, so sp2 to get to 3. So those are sp2 hybridized orbitals that are overlapping with the hydrogen s orbital. But when we do sp2 hybridization, we have a leftover p orbital. And that unhybridized orbital is what a strange bun around a hot dog to make our triple bond. What do you often get asked? Often student question. You're going to see things like that. First off, their color, so no. Hard to see what's going on in black and white, so no. What you often get asked is what is the hybridization of an atom? Remember, just add the electron groups together and then start with S and move your way up. And another thing you could be asked is how many sigma or how many pi bonds there are in a particular molecule. So for our C2H4, every type of bond consists of at least one sigma bond. If you go back to that table we just filled out. So just count the bonds. We have 4 single bonds connecting the hydrogens to the carbons, and we have a double bond in between the 2 carbons. So don't count the lines, count the bonds. So we have 5 sigma bonds. To make our double bond, we need 1 pi. So in that molecule, there are 5 sigmas and 1 pi. That is the most often asked question besides what is the hybridization of this particular essential atom. So over here, for our acetylene, we have 1, 2, 3 bonds. 3 sigma. To get the other 2 lines between the carbons, that's representing 2 pi's. Notice when you do that, good way to check, count your lines, and then add your numbers together. For our C2H4, we have 5 plus 1 is 6. Well, we have 1, 2, 3, 4, 5, 6 lines. In our acetylene, 3 plus 2 is 5. We've got 5 lines. It's a good way to double check. Any questions? This table might look familiar. On your page, it has the last column unfilled. This is to emphasize that really the hybridization goes with the number of electron groups, if you're good with counting those. If you're better with base structures, well, it goes with the base structure as well. But the hybridization does not change when you're replacing the eternal atom with a lone pair, meaning for all the variations, it's all the same hybridization. And we didn't do the trigonal bipyramidal like our phosphorus pentachloride, but we need 5 attachments. Well, sp3p. S with 3 p's, and with 3 p's and a d gives us 5. Any questions? Number 37 is another one, practicing counting your sigmas and your pi's. So I'm going to give you the answer, and I want you to practice it in case you think you need that practice. So in number 37, there are 4 sigmas and 1 pi. You should also be able to get the hybridization BGAP. Have you thought of any questions? It would have been nice to get that point on Friday, but we had to do other evaluations, so I had to kind of cut the topic in half. We are now going to move on to the next chapter if there's no questions. Please recall that last section, molecular order theory, I'm not just skipping it, it's not taught, it has been taught for quite a long time. In terms of this chapter, if you had watched the video, you saw that. There's something a little different on the video one, because I don't always have to do this. This semester I just ended up talking a little slow. So in the video, the properties of liquid, you were asked to read that for general understanding. I'm not going to give you 2 compounds and ask you all kinds of weird things, which one has a higher surface tension or this or that. It's just covering how our intermolecular forces are actually being represented or shown to us in the macro scale world. What I want to make sure to cover is the intermolecular forces for mixtures. This is table 104 again? That's where we pick up in Gen Chem 2 and most other places if you're going somewhere else, pick up right in the middle and we do a little review of intermolecular forces for mixtures, because chapter 13 is properties of solutions. So it's a really nice bridge right now. Then we definitely have to get the phase diagrams in. Depending on time, we might talk a little bit about the phase changes, but that's actually all review. Physical changes, right? Vaporization, condensation, things like that. So I'm asking you to go to page 306. Hopefully the other stuff you would have been able to fill in from the video. So far. There we go. So number 15, page 306, about halfway down is where we're picking up. Potterly mono mixtures, this is more on your viewpoint. If you're looking at an exam booklet, how do you know you're looking at a mixture? Remember, you would have at least two different symbols, maybe 3 or 4. But not all the symbols would be the same in order to have a mixture. You, of course, would have to have at least 2 pure substances mixed together, whether it was heterogeneous or homogeneous. Throughout this section, we're going to be able to see how inelectric forces and size actually affects the solubility of things. So we're going to talk about not only the new terms for what new attractive force is being created when you put solute into solvent, but then we're also kind of connect this with solubility. When we think about solubility, we have to think of it kind of like a substitution process, which is why they have 4 water molecules at the bottom of the page. Meaning, we know in a liquid, things aren't really, really tight together. There's some space between the particles. And if what we're trying to dissolve is of similar size and will interact with our solvent, then it will fit nicely into the spots between the particles, in this case the water particles. If what we're trying to dissolve is really big, you have to think about energy has to be used to push the solvent out of the way. Things tend to be less soluble then. This is just a structural formula, not Lewis structure because there's no lone pairs, of water molecules interacting with formic acid, kind of what you're asked to think about in number 16. Although the formic acid is a little bit bigger than water molecules, it's still fitting nicely in the spots or spaces between the water molecules, and therefore, because it has similar inelectric forces, right? We have a polar molecule that has dipole and hydrogen bonding. We have a polar molecule that has dipole and hydrogen bonding. Formic acid is therefore soluble in our water. Another image I have goes with the top of the next page. Some students like these because the color helps you. Remember, red is negative. Yours are black and white, by the way. Blue is positive. So we also get our water molecules orienting themselves in a certain way around that formic acid molecule so that we have opposites attracting. From this water here, near the oxygen, we have the red. Well, the formic acid, we have a little blue area. Therefore, we get some interaction there. On top, the blue area by the hydrogens of the water is interacting with the red by that double bond oxygen. Again, although the formic acid is a little bit bigger than water, it fits nice because it attracts as well. So there's the whole idea of light dissolving light. In part B, on page 307, here's the size idea again. I think sometimes it's brought up a little too much. I know I tried to do it. So this gives you a little place to think. How does the size of an incoming molecule affect the substitution, meaning placing this into our water matrix, basically? If it was really big, the water would have to move out of the way, which is not really a favorable thing, which is why oil doesn't mix with water. Oils are really big, plus they don't attract the water molecules because in general they only have dispersion. Most of them are nonpolar. We're going to go through the flow chart to first, down the left-hand side, to think about the new terms we're using, and then down the right-hand side to think about the solubility part. Are there any questions before we do that? After we do each side, we're going to do one side, and then go to the next page, do a practice problem, and then we're going to do the other side, and go to the next page, do a practice problem. Over the years, I just found that works best. So, if we want to think about the intermolecular force between solute and solvent, this is really important for your next semester. Whenever you dissolve something in a solvent, not only do you have the original intermolecular force still present, but you're actually creating a new attractive force between your solute and your solvent. So we have to think about not only the originals, but what else we're going to be creating. Of course, everything has dispersion as long as there are electrons present. However, when you're thinking about solution, what's in the parentheses is really more important, or what I have duplicated underneath. If we're mixing a nonpolar compound with a polar compound, meaning our solute and a nonpolar compound. Our solute and solvent are both nonpolar. We are going to create a new attractive force, but it's only based on those induced and temporary dipoles for our dispersion forces. So therefore we call it induced dipole, induced dipole. The hyphen in between is separating your solute from your solvent. Means the phrase in front of the hyphen is for one of your compounds, the phrase after your hyphen is for the other compound. So if you see induced dipole, hyphen induced dipole, that's telling you I have two nonpolar things here because only force they have is dispersion, and that's due to temporary dipoles, inducing dipoles, and other things. If we decide to mix a nonpolar substance with a polar substance, we're going to have a different new attractive force created. Because the one that's polar also has dipole forces. We would then call that induced dipole for the nonpolar thing, hyphen dipole for the one that's polar. Moving down the table, if we mix a polar substance with a polar substance, since they both have dipole interactions, we would call that dipole-dipole for the new attractive force created between the solute and the solvent. You use a lot of ionic compounds this semester in lab, so the last two are dealing with ionic compounds getting mixed in something else. The first one is trying to mix an ionic compound with a nonpolar substance. I mean, if I tried to, let's say, I don't know, put some sodium chloride into some benzene, something like that, something that's just only has dispersion. Well, again, the hyphen is separating what you're mixing. If it's ionic, we don't usually do intermolecular forces with that. We just say it's ionic, right? So ion is telling us we have an ionic compound. Hyphen, induced dipole, is telling us we have a nonpolar substance. The most common solution you made is putting something like sodium chloride in water. Well, water's polar, so therefore the induced dipole doesn't work for that. We would have then ion dipole forces being created. And this attraction between solute and solvent, no matter what variation it is, actually leads to many different properties of solutions. Any questions before we do our practice problem? So we're going to go and do number 18 on the next page, because that is titled, What are the IMF that exist between substances? I've reproduced our little table here, because I know you have to change page. So if we're going to mix methanol and water, good practice is to make sure that we have our intermolecular forces taken care of, the separate ones, because then we can think about how they're going to interact. So at the bottom of the slide, I have the methanol, I also have the water. Can these two things hydrogen bond with themselves? We have OH bonds, right, in both. So if something is hydrogen bond, that means it also has dipole force, and then it also has dispersion. Many students, or most students, can recognize hydrogen bonding from Lewis structure, right? You're looking for the special types of bonds, OH, NH, or FH. If we have hydrogen bond present, everything else is also present, meaning that dispersion, dipole, and hydrogen bonding for each of those. Since hydrogen bonding is a special type of dipole force, the new attractive force is simply called dipole-dipole, in addition to dispersion, which everything has. Any questions? You wouldn't be asked to fill out a whole table, you'd just be asked multiple choice. What is the new attractive force created when this and this are mixed? So if I create mixed methanol and water, the new attractive force would be dipole-dipole. What about our salt in our water? Water is polar, salt is ionic. Is there a question? Right here or see? Oh, good. You're answering my question. Thank you. Yes, it would be ion dipole. Again, we usually don't do intermolecular forces for ionic compounds. We just say it's ionic. Our water, of course, has dispersion, dipole, and hydrogen bonding. But because hydrogen bonding is a special type of dipole force, we just center on the dipole. So yes, you're correct. Ion dipole would be the new attractive force that's created between the sodium chloride and the water. Again, leads to chapter 13 and many properties of solutions that become coming because of the fact that we're creating another attractive force. Any questions? I think the hardest part of it is just deciphering the hyphenated terms. Remember that induced dipole simply means dispersion. That's the hardest one. I don't know why they didn't just call it dispersion way back when. We're going to go back to our flow on the prior page to think about the solubility now. Remember, like dissolves like. We already talked a bit about this. We want our molecules to be able to fit nicely into the matrix of our solvent, and we want to have attractive forces between these two different compounds, meaning we want to determine both the intermolecular forces for the substances to see if they're similar. And then we're going to think about the size. measure things? No, they're close. So they don't have to be the same, although I know the word same is there. Are they similar or are they vastly different in size? Then we have to think about, well, we want to have the size and the attractive forces similar to have something be highly soluble. Well, if both of them are the same or similar, then we would classify something as soluble. Remember, hydrogen bonding is a special type of dipole force. So if something can hydrogen bond, the other one can't, but is polar, that's similar enough. If one of these, wrong click. If both of these are different, oil and water. Oil's really big, water's really little. Most oils are not polar, water's polar. Then we call them insoluble. And I always mention oil and water because we all can relate to that. We know they don't mix. If one of the characteristics, IMF or size, is the same and the other one is different, we call that partially soluble. And we'll actually look a little bit at what that means. Before that, we're going to just do a little table on number 17 on the next page, unless there's any questions. So this goes with number 17. Again, I reproduced how we have to do this. And methanol water is, again, our first one. So we already know the IMF for those. We know they're both the same. There's our structures again. So we know we have dispersion, dipole, and hydrogen bonding for each of them because they both have an OH bond. The size, do you think these are similar or different? They're close enough. They're both small. Methanol is actually infinitely soluble in water. So that's what I like to give that example because they don't have to be identical in size. They just are similar in size. These happen to be identical in intermolecular forces, but they wouldn't have to be. If the hydrogen bond was missing from one of them, it would still be close enough. Methanol ended in OL. Well, guess what? Butanol ends in an OL, which means it also has an OH bond, as you'll learn when you take organic chemistry. Those are alcohols. Anything ends in OL has an OH bond, meaning for our butanol, although now bigger than before, a longer carbon chain, will still have the same attractive forces as the water does. Dispersion, dipole, and hydrogen bonding. However, now, I don't know if I can call that the same as far as size. One's larger, one's smaller. So I would call that different in size and therefore partially soluble. The IMF is the same, but the sizes are different. Although heptanol has a 7-carbon chain, a lot longer, it still has to be somewhat soluble because the intermolecular forces are the same. We still have an OH bond. So we still have the same intermolecular forces, meaning we're going to be at least a little soluble. Our sizes are definitely different, large and small, but we would still call this partially soluble. We will investigate what that means a little bit in just a second, unless there's some questions. I have added this. This does not, and it's not in the lecture activity book because students have really problems understanding what partially soluble meant. First, near the top, we don't even have our methanol there. Notice we have a 3-carbon chain. Okay, our butanol had 4 carbons, and even with a 3-carbon chain, the size is close enough that we call that infinitely soluble or miscible, meaning our methanol would be above that even. As our carbon chain starts to grow, our size is too different from water then. Meaning everything with a number there is partially soluble. By partially soluble, we mean some of it dissolves. Just not infinitely. By infinitely, or say miscible, we can put as much of that top alcohol, which is propanol, into water, and it will never separate. For the others, we'll get separation, meaning layering, meaning creating a heterogeneous solution once we get up above a certain amount. And notice how that amount is getting larger as the carbon chain gets longer, as the size difference changes, or as the sizes get more drastically different than water. What would these look like? Our miscible would be homogeneous. We wouldn't know that the propanol was there. For the other ones, as we cross chain gets longer, we would be able to dissolve less of it, meaning we get a layering much sooner. So just to give you a better idea of what we mean by partially soluble. Although for the two on our, the second two on number 17, we just wrote the same words, partially soluble. It would of course be different depending on how long that carbon chain was. Hopefully it makes sense. The heptanol, we'd be able to dissolve less of it than the butanol. By the way, our butanol is the one that has 8.88 by it, and 1, 2, 3, 4, 5, 6, 7. Heptanol is the one at the bottom. Any questions? In which case, the next section is those property of liquids that we were asked to kind of just read for some general understanding. Meaning we are going to page 322, make sure we get phase diagrams in, which I know is on your final exam. I know it's a lot of jumping around, like happens almost every semester, actually happens most semesters. Let me get to that. Yes, I want. Oh no, one more. There we go. I'm going to go to that. 322 at the top. It asks you what is a boiling point in terms of base pressure. I want to give you a clear definition of what boiling point is. Boiling point is, of course, the temperature at which, so BP is the temperature at which the vapor pressure equals external pressure. Ooh, that easy. Now I'd like to give you a visual without actually giving you a visual. Your boiling water makes mac and cheese, or whatever your favorite thing is. The bubbles in the water are containing gas, right? The pressure inside those bubbles, when they start to come to the surface, is equal to the pressure in your kitchen. So that's what I mean by the vapor pressure of the substance equals external pressure. That's when you get boiling. And of course, that's for depending on the external pressure, you can have different temperatures at which things will boil. If we know a specific pressure, 38A, we call that a specific name. Normal means 1 atm, meaning the normal boiling point is the temperature required, oops, bad there, for a vapor pressure of 1 atm. Meaning, if you're asked what's the boiling point of water, what do you usually say? 100. It's only 100 degrees Celsius at 1 atm. Meaning, if you have different pressures, you will have different boiling points for water. Which is why on many cake mixes, they have high altitude instructions and things like that. When we're thinking about how, let's say, boiling point changes with different pressures, that's when we're starting to think about phase diagrams. So number 38, they actually have a definition for phase diagram for you. It summarizes the conditions under which a substance will exist as a solid, liquid, or gas. We're going to first focus on this transition between liquid and gas. So this is a typical phase diagram for something like water. We'll look at other substances in just a second. This curve right here, going between liquid and gas, this consists of all kinds of temperatures that the water will boil at different pressures. So if we say right here, going across my arrow, say, that's 1 atm. That means down here, that would be 100 degrees Celsius. But if your pressure was lower, then your boiling temperature will be lower. If your pressure was higher, then your boiling temperature will be higher because the curve is upward sloping. What for water occurs at 100 degrees Celsius, 1 atm, the normal boiling point. What is this called? Sorry. It boils. What is this called? The normal boiling point. Sorry. What happens when temperature changes? We're going from liquid to gas. If we're keeping the pressure constant and you're thinking about changing temperature, we're either going towards the gas or towards the liquid. For us as humans, that's easy to understand because we generally live at a constant pressure. When you're thinking about what happens this way. Okay? So if we decrease the pressure, go down to the y-axis, we're going from liquid to gas. If we decrease the pressure on a liquid, we can make it vaporize without changing the temperature. So of course, if that pressure is increased, we would be going up, and we of course could make our gas liquefy. We're pushing the gas particles really close to each other. Then they start to interact with each other, and then they start to condense. The same thing can be thought about and happening when we're thinking about freezing. So the curve here between solid and liquid is all the different temperatures at which our water will be freezing. If we're at 1 atm, oh, that's a really bad straight line. That would be at 0 degrees Celsius. But if we have different pressures, we're going to have different freezing points. Again, the normal freezing point would be at 1 atm, the one that you usually think about, 0 degrees Celsius. If pressures increase on ice, what happens? Think about if you're on that vertical line that was really shaky, and you go up, you're actually going from the solid to the liquid. Well, that makes sense. That we have a big crystal structure for our ice, right? If we increase the pressure enough, we're going to crush it. To crush that crystal, it liquefies. So if the pressure in ice is increased enough, you actually crush the crystal lattice, you liquefy it, or you melt it. You go from solid to liquid. We have a couple of main points on our phase diagrams. I have actually the terms for it. I forgot to click, sorry. We went through that. Triple point is where all three lines intersect. So this one I drew here, right there. That would be our triple point. Meaning, if you have the exact right temperature, x-axis, and pressure, y-axis, to be at the triple point, you have a sample of a substance, let's say water, that is solid, liquid, and gas all at the same time. Which is kind of hard to think about. For water, this occurs at a pressure and, well, temperature we get close to, but a pressure that we don't live in. 0.006 atm and 0.01 degrees Celsius. You don't need to know the numbers. Which is the reason why we don't experience this and it's unfamiliar with us is we cannot exist at 0.006 atm without a breathing apparatus at least. Another point that we need to make sure you understand what it is I call it the critical point. The term here is having you think about the x-axis and the y-axis. And sorry for forgetting to tell you, we did turn the page. We're on page 323. Our page has changed. I actually have a point right here. This would be our critical point. And the temperature would be, if you went straight down to your y-axis, or x-axis, sorry, the pressure, critical pressure, needs to go straight over to your y-axis. Above this point, a gas cannot be made to liquefy no matter how high the pressure. Also, it's the highest temperature at which a substance can exist as a liquid. It's actually called a critical fluid up here. It's not liquid, it's not gas, it's kind of something in between, it's a weird area. Notice this isn't something that we would experience if you look at that pressure and that temperature. 217.7 atm and 374.7 degrees Celsius for water. The big thing is if you have a phase diagram that's labeled with things. Note the end of the one line is the critical point, and where all three of them go together is the triple point. That's what you need to know. I know about what time it is, but I want to show you something that's not like water. It all has to do with that curve. If it's this way versus this way, kind of. So if you're given a phase diagram that isn't typical for water, slanting back instead of slanting forward, that tells you it's something else. And unfortunately, I need that curve too much. I want to go straight. There we go. So if we increase the pressure on a liquid here, we would actually end up making it to the solid, right? Whereas here, if we increase the pressure, we would make it liquefy. Most things, if you have liquids, say elemental liquid, and you push it together, you can make it to a solid because those solids have all their atoms really close to each other. This kind of comes up in number 43. They give you one for carbon dioxide, and slant is different. actually have an example on page 324 in the selectivity problems of one that doesn't have a label. Meaning if you're over cold temperatures, it's a solid. As you move, it gets warmer, so you go to liquid, then gas. Also, just know where the triple point is, where the critical point is. That's the extent of what you really need to know about phase diagrams. Depending on your major, you might take a whole semester of a class that I don't like teaching, but I have taught, where you look at all kinds of phase diagrams for substances and mixtures and all kinds of stuff.